Welcome everyone to the first webinar of 2023. I'm Tony Roskilly. I'm Professor of Energy Systems at Durham University and a Director of Durham Energy Institute. This event is organized by the APSRC Network, H2 Network Hydrogen Fuel Transportation, and is part of an ongoing series of webinars looking at different aspects of hydrogen research in the transport sector. This webinar, we welcome two speakers that will present their findings on hydrogen-related research work. When we talk about hydrogen, that also includes hydrogen carriers as well. Our colleagues are from Brunel and Nottingham University, and I'll introduce them. Our next presenter is Professor Alasdair Cairns. He's Chair of Propulsion Systems at Nottingham University. He's going to present on the Marion NH3 project. Professor Cairns is Director of the Powertrain Research Centre at Nottingham and has almost 25 years experience in light and heavy duty engines, decarbonisation fuels and electric hybrid propulsion systems. In his earlier career, he was involved for 10 years as an engineering consultancy with Cosworth and Mahler powertrains, and he managed large collaborative R&D programs with those companies. He currently is the program director of the Marion NH3 project, which is investigating the potential of green ammonia to fuel and decarbonize commercial shipping. So over to you, Al.
Thanks very much, Tony. So the presentation's entitled Ammonia and Hydrogen IC Engine Research at Nottingham. So I thought I'd just give an overview of the work that we're doing in the lab at Nottingham. So in terms of the contents, talk a little bit about the group. We've got quite a large engine group at Nottingham. Talk about some of the options for fuels, just following on from Xingyan there. What are the alternative fuels and what are the trade-offs that we have to have with those fuels when we can't use electrification. A little bit about some of the complementary engine studies that we're working on at Nottingham with some of these new fuels, and then a summary of all of that. So I look after what's called the Powertrain Research Centre at Nottingham. So we've got quite a large and active group of engine researchers. There's about 15 to 20 active researchers in the group. The main thing that we work on is decarbonised fuels and heavy-duty engines, because engines are going to be around a long time after me. I think it's fair to say, especially for applications where it's hard to decarbonise. The problem is the fuel, not the engine per se. And actually, the technologies that we work on at Nottingham, we try to focus on what I would call advanced retrofit technologies. So that means cleaning up existing large diesel engines that typically remain in service for several decades, for example. And as you can see in red, there's typically a trade-off with any engine between making it clean, so cleaning up the pollutant emissions, and also maintaining a high thermal efficiency, so getting sufficient work out of the fuel. And we work on novel combustion modes and novel engine cycles to try and improve that trade-off. So on the screen, you can see some examples of the facilities that we've got. The bottom left shows a single cylinder research engine. So that can be operated at very high speeds and loads. In the middle, we've got dual fuel generator set or marine engine. You can think of that one as being. So that's a diesel engine that's been converted with a second cleaner fuel. And we've also got optical engines and combustion chambers. So we can cover all the things that we need, really. So that's a little bit about the group. So if you look at the options for the fuels, without going into too much detail on things like cost, if we just look at the practicality of different fuels, what you can see in the graph there is the energy density on a volume basis of the key competing fuels. So the first point to note, diesel there at the top is energy dense. There is no better way to carry energy for transport than a liquid hydrocarbon. That's why we've used them for hundreds of years now. And it becomes quite clear, actually, when you see it visually like that, how superior they are in terms of energy density and ultimately range of the transport, or the amount of goods that the transport can carry. So we have to decarbonise, and ultimately we have to stop getting carbon out from under the ground. That's the inherent problem we've got. So when we look at the options we've got the so-called carbon fuels shown in grey. And for the last couple of decades, there's been a lot of research done on all of those fuels, but particularly biofuels. So that would be bioethanol or methanol, the alcohol-based fuels. And they're very attractive. And in fact, we use ethanol in standard pump grade gasoline. There's 10% of it in the gasoline in the UK. The problem with it is it doesn't scale up. Biofuels are limited on a global basis. And when we look at net zero, it's a double whammy, really, because the feedstock that's used for those fuels will have to be diverted towards aviation, or so-called sustainable aviation fuel, because there's no other choice in practical terms for aviation. It's a very difficult sector to decarbonise. So that leaves us with the green fuels. So these are synthetic zero carbon fuels that we can potentially make using renewable energy. You could argue actually that methanol and ethanol could also be shown in green. So you can make synthetic methanol from renewables as well. The problem with that, it still carries carbon. You have to either capture it, and you also have to make the fuel using some form of carbon. There's a lot of interest at the moment in synthetic methanol for things like marine, heavy power generation. But when you look at net zero, you still have a problem with carbon. So because of that, there's now, in the last 4 to 5 years, there's been an explosion of interest in fuels like hydrogen and ammonia. So if we first look at ammonia, ammonia is attractive as an energy carrier. It's a very effective carrier of hydrogen. That is the main benefit of ammonia. When we look at it as a fuel, it's got very poor combustion characteristics. It's toxic. It still releases emissions of NOx. And we also have to make sure that we don't release any of the ammonia in the tailpipe or the funnel from a vessel. So there's a lot of challenges around ammonia, but if we can overcome those challenges, it's very attractive because we can carry hydrogen around very effectively. Ammonia is a liquid if you compress it just to around about 9 bar, and it will stay a liquid. You can put it in a tank and leave it for years if you so wanted, and come back and use it when you want. Whereas with hydrogen, it's very attractive from a combustion point of view, but there's problems with storage and carrying it around. So we're actually working on all the fuels because we think there's a place for all of them and we'll need them all to get to net zero, but they all have their individual challenges and none of them is a silver bullet. When we specifically look at ammonia, there's a few other points to think about. So usually with ammonia, a lot of feedback that we get is it's toxic, it's very dangerous, and it is. But we already do move a lot of ammonia around the world as fertilizer. It's the main fertilizer we use globally. And what you can see on the heat map there is the existing port infrastructure around most of the major shipping routes across the world, showing where ammonia is. So for actually moving ships around, there's a lot of existing infrastructure we could tap into. The problem being, we move ammonia around the world in ships at the moment, and we do it using diesel. Seems highly counterintuitive. So there's a lot of interest in actually converting these ships to use the ammonia as the fuel. And if you're converting the infrastructure to be more environmentally friendly, we can use it for other things as well. A key point to note, though, is when you look at this heat map, the ammonia that's made at the moment is mainly sourced using natural gas or a small amount of coal. And that's very carbon intensive. So while it's attractive to look at new uses for ammonia, and we need to do it, a key point to note is we also have to clean up the existing usage of ammonia away from transport and do that in parallel. So looking at using it as a new fuel for transport. To give you some context, the amount of greenhouse gas in the fertilizer industry is about equal to the amount of greenhouse gas in the maritime sector. So they're both large problems that need to be addressed. So that's a little bit of background on ammonia. So what are we doing at Nottingham? We've got various projects now underway looking at using ammonia, hydrogen and methanol now as an alternative fuel. One of the projects we've got, which was why Tony kindly invited us to come and talk to you, is a new programme grant, which we've called Marion NH3. So this is funded by the EPSRC, the main funding body for UK engineering research in academia. And it's just started. It's quite a large project, but what we're trying to do is look at the optimum end use of ammonia across the maritime sector. And the dartboard figure that you can see on the left, the bullseye shows what we're actually trying to do. So instead of being engineers working in a silo, what we're actually trying to do is work up the technologies and the right policy guidance and hopefully get it right first time. The ultimate goal is to understand where ammonia can be applied and also where it shouldn't. There are other energy vectors where ammonia won't be the favoured solution. So it's a multidisciplinary thing. There's a team of about 15 academics in total and an equivalent number of researchers. The colours show the different themes that we're working on. So theme 1 in purple, acceptance. Theme 2 is fundamentals. And theme 3 is how you actually apply the fuels. And then around the periphery of the diagram, we've got a number of boxes and they show the work packages that we're trying to address. So in purple, from 6 o'clock clockwise, we're looking at the legislation around ammonia, how we move it around in marine, can we learn from refrigeration, the socioeconomics, the acceptance criteria around it, how will crews react to using this fuel, the life cycle impacts, so from cradle to grave, what's the true greenhouse gas impact, fundamentals, how we move the fuel around a vessel, how we burn and clean up any remaining emissions. And then in blue, how we apply it. So can we retrofit it to these large marine engines that are typically in service for 3 or 4 decades, some of them? Or should we just go straight to new, more advanced engines that could potentially work well with ammonia? And how does it look overall from a system perspective? And we're very lucky. We've got quite a wide number of industry and policy-making partners. So one of the things I'm very passionate about in the research we do in our group is making sure it's aligned with UK PLC. It's a duty of care to make sure we're using UK taxpayer money to do that. So what we tried to do in this one was cover a wide cross-section of the UK supply chain that's relevant to using ammonia in IC engines across marine and possibly other sectors like power generation. And the long and short of it is it's most relevant to 4-stroke engines. So when we look at some of the larger ships that are powered using engines by companies like Wärtsilä and MAN, they don't have large engineering centres in the UK. So we've focused on the opportunity for the UK, and the logic being, if we can get ammonia to work in a 4-stroke engine, it's easier to get it to work in a lower speed 2-stroke engine. So that's the reason, or the reasons why we've focused it as we have. In terms of the technologies that we're looking at, so a programme grant is supposed to be flexible funding. So after 18 months, you review what you're doing and change direction if something's not working. So for the first 18 months, we're looking at what are the engine technologies that we could use. And you can see an example shown in the cartoon there, a dual fuel engine. So a dual fuel engine is where you take a secondary cleaner fuel and inject it into the engine's intake system. So the clean fuel is shown in blue. Otherwise, the engine remains as a normal diesel engine. And the great thing about dual fuel engines is you can revert back to diesel only when there's no cleaner fuel around. So it's a retrofit solution, well suited. We've also got a couple of novel engine technologies that we're working on with some of our industry partners, jet ignition, and I'm going to talk a bit more about that in the last part of the presentation. And the Dolphin N2 engine is a very novel split cycle engine that's been developed in the UK. It's giving very high promise, 50% efficiency and very low NOx. And that's being researched with one of our partner universities at the University of Brighton. We're looking at the after treatment. So even if we can burn it, we have to clean up the emissions. We have to make sure there's no ammonia slip out from the engine. And actually, we might want to crack a little bit of hydrogen from the ammonia fuel to help overcome the bad combustion of ammonia. So we're looking at that as well. Could you use the engine's waste heat to crack some hydrogen and help improve the burn? And as I said earlier, the life cycle and scalability analysis, and also the acceptance criteria, the socioeconomics impact around using a fuel that's toxic. So that's a very brief sort of overview of some of the objectives we've got. What I wanted to do for the last part of the presentation was actually show you some of the engine results that we've got. So whenever you have a new fuel, as an engineer, it's important to have a certain degree of skepticism over its operation and be realistic about it. And actually, we all had a healthy degree of skepticism around ammonia, but some of the results we've seen already are very encouraging in the engines that we've been running. So what you can see on the screen is a picture showing our thermodynamic single cylinder engine. So you can think of this as being a typical automotive spark ignition engine. So this is typical of what you'd find in a modern passenger car fueled with gasoline, which is a very similar type of engine to a modern outboard engine on smaller boats and marine vessels. It's a state of the art, and we've taken this engine and retrofitted cleaner fuels to the intake system in effect. So what you can see on the left-hand side is a cartoon illustrating a slice through the engine's geometry. And the reason I've included it is it shows you how we introduce different fuels into this engine. So under normal circumstances, you can see the air gets breathed in the intake port, we call it the pipe, into the engine and tumbles into a bulk air motion there. We call it tumble, the circular motion of the air, and that makes the air very turbulent. And in most modern engines will then directly inject gasoline fuel into the air, and that's what's shown by the orange arrow. So there's a direct fuel injector that's injecting E10. E10 is gasoline. It's gasoline with 10% ethanol in it, and that's what we use in the UK at the pump. So we've retrofitted ammonia to the engine's intake system. So the green arrow shows where we inject gaseous ammonia in with the incoming air. So that's one of the simpler ways for introducing ammonia into an engine. It's already in gaseous form. So what we have looked at in our initial experiments is we always start the engine using E10. We run it up to a fully warm condition, and then we co-fuel the engine. So we start to introduce some ammonia and we back out the amount of E10 until hopefully we're running on 100% ammonia. Keep in mind, it's a very bad fuel in terms of being a very slow burning fuel. So our initial experiments focused on just one engine speed and load and trying this out. So that's shown in the table. So the speed was 1800 RPM, which is a typical, reasonably high speed for something like a marine application or a stationary genset. And we operate the engine at about half load. So 12 bar net IMEP. So that's about halfway up the torque curve. And at each log, we always operate the engine stoichiometric. So in other words, as we add ammonia, we take out gasoline and keep the ideal mixture of fuel and air. And we always re-optimize the spark timing to give us the best efficiency at every point. And when we did that, you can see the engine out emissions shown on the screen. So the y-axis, if we look at the left-hand top graph, shows the CO2 in percent in the exhaust coming out of the engine. The x-axis is the amount of ammonia we were able to run. So 0 on the x-axis means we're running on 100% gasoline. 100 on the x-axis means we're running on pure ammonia. And what you can see is we were able, at this speed and load, to run on pure ammonia. Now, if we assume that that ammonia was made using renewables, electrolysis, the top three graphs show that we fully decarbonised the engine. So in the middle, the unburnt hydrocarbons go towards 0. There's no hydrocarbon in the fuel. On the right-hand side, the partially burnt carbon monoxide has gone towards 0. They're both slightly above 0. They're actually at the accuracy of our analyzer. So the only remaining small amount of hydrocarbon is due to the engine oil. And the bottom line is you can ignore it. It's next to nothing. So the punchline really is you can fully decarbonize an engine by decarbonizing the fuel. So that's the first thing to know. The other thing to know, in the bottom left-hand graph, this shows values of nitrous oxides. It should say NOx on the y-axis. It's all of the species. When people talk about ammonia engines, they often sometimes think they have a problem with NOx. In our case, we've halved the engine out NOx by just switching the fuel. The challenge is trying to understand the different species in those NOx. There's different forms of chemical species, and we're trying to understand those now at Nottingham, but it still looks encouraging. We've halved the engine out NOx just by changing the fuel. So that's the engine out emissions. It's a positive start. So the next thing that we looked at was trying to move around the engine's speed and load operating map. So this is what's shown in the first figure here. So when you look at the graph, the x-axis is the speed of the engine. The y-axis is the engine load. And you can see there's a lot of data at 12 bar. So that's roughly half engine load. And the numbers in the bubbles are the maximum percentage of ammonia that we were able to run. So where it says 50, on the figure, it means it's 50% ammonia and 50% gasoline. So as we've come down in load, we've had to use some gasoline to maintain a stable combustion. So the first thing that we did was increase the engine's compression ratio, which basically means how much are you squeezing the air before you combust it. And we have quite a lot of headroom to increase the compression ratio with ammonia because it has a very, very high anti-knock rating. You're not limited by combustion knocking when you use ammonia. So we did a subtle increase in compression ratio, and we increased it from a value of about 11.2 up to a value of about 12.5. And when we did that, there's a lot more 100s showing on the map. And we think this is really encouraging because a simple mechanical upgrade has enabled us to capture much more of the speed load map. If I was to superimpose a low load limit line on the figures, you can see we're able to operate the engine at lower loads. And that's the ultimate goal, really. We want to be able to run this engine on 100% ammonia so that we've fully decarbonised it everywhere. We're not quite there yet. So there's other things that we're looking at in parallel, including cracking a little bit of hydrogen to enable us to leave it on otherwise just ammonia fueling. So that's the first sort of set of results we've had. We haven't actually published these yet. They'll be published this year. As well as looking at normal spark ignition, though, one of our key partners at Nottingham is a company called Marla Powertrain. And for the last 15 years or so, they've been working on a very novel engine combustion system. They call it jet ignition. Actually, a version of this is used in modern Formula One engines. It's a spark ignition engine, but what we do, as you can see shown on the figure, is we recess the spark plug at the very top of the picture there into its own miniature combustion chamber. And we call that a pre-chamber, and that's shown in the brown colour. So what we do is we initiate combustion in the pre-chamber, and it's only a partial combustion event. So normally what happens is you get a very fast part burning, and it creates a cocktail of very reactive and partly burned combustion species like hydrogen, H, O, and OH. And those species then get spat out across into the main combustion chamber. And that's what you can see illustrated by the white clouds, if you like. And ultimately, what they do is ignite the rest of the charge. And in the pre-chamber, there's only about 5% of the charge. It's a small volume. So what you're actually doing is using these highly reactive jets to create a much bigger flame zone. And that means we can run the engine very efficiently. It runs with a very fast combustion, but we can also run the engine very lean, extremely lean. And we're working on optimizing this at the moment with ammonia, but we've already tested it just in the last couple of weeks with hydrogen. So using this type of combustion system with hydrogen. And when we did that, what you can see on the screen is a map of the engine out NOx. So this is the only remaining emission or pollutant emission from an engine when you've decarbonized the fuel. The x-axis is how lean have we gone. We call it lambda. So a value of 2 is twice as lean as normal. A value of 3 is 3 times as lean. The y-axis is the engine load. So this is about a third load in an engine. This would be representative of a truck driving around a city. And the punchline is the engine out NOx were 3 parts per million. That's without any after treatment. So when you think about hydrogen internal combustion engines, they also do not have an NOx problem if you use an appropriate combustion system and you size them properly so they don't have to spend their time up at much higher loads, make them bigger, for example. So that's also quite exciting, and we're carrying on working on that as well as the ammonia work. So to summarize all of that, that was just a snapshot of some of the work that we're doing on Marion NH3. So engines will remain critical for large, heavy transport applications where batteries have an energy density issue. However, it's important to stress that there is no silver bullet. All of the fuels that we looked at the start of the presentation will be needed if we're going to decarbonise more quickly. We need them all. We just need to understand what's the best use of each of those fuels. They all have a part to play. Biofuels, however, will probably, the feedstock needs to go towards aviation, which is very challenging otherwise. Hydrogen is really attractive from a combustion stance and an emission stance, as we've seen. But the problem is moving it around, how you store and move hydrogen around over long range. And that's where ammonia comes in. And it's only because of that problem, I would say, with hydrogen. So ammonia is attractive as a hydrogen carrier. If we're carrying it around as hydrogen, we should try and understand if we could use it directly rather than being inefficient and converting it back to hydrogen for end use. What we've seen at Nottingham so far is you can use it as a 4-stroke engine fuel. It's not restricted to 2-stroke. It would be very unlikely, though, that you'd be able to start an engine from cold using ammonia from what we've seen. You'd still need to start the engine and pre-warm it on a second fuel. And the NOx emissions need full characterization. We need to fully understand full impact of all of that. So that's the end of the presentation. Thanks for listening. I'll pass you back to Tony.
Thanks very much, Al. Great presentation.